Okay, so let's think about this. Now I want to think about the displacement field in 2D. So in 1D, things could only move left and right by this, and things was only a function of one variable x. Okay, so my expectation in 2D would be that things can move left and right as well as up and down. And so I would have one field u to give me a description of how things moves up and down, left and right. Okay, but now I can look at points on an x and y scale. So things are now in 2D varying as a function of x and y. So if I just draw for myself to make it clear as kind of a square, this, and let's say we put some nodes down at the edges of the square. Okay, so why the edges of the square? Well, on the line we put the nodes down at the edges of the line, for instance, and maybe in the middle. So we could maybe think that similarly in this 2D case we might want to do something like this. Put the nodes at the edges and in the middle. So that's maybe an equivalent of a 2D kind of thing in 1D. But this node, and each of these nodes can move left and right, up and down. Actually, each of these points, but we're going to have a function of how every point in this cube can move up and down and left and right by having sort of values at these discrete nodes that will dictate how that field essentially would then essentially look like, or to manifest a version of that field. Okay, so this can move left and right, and that is what this u field will describe. But if I move towards here, it can also move left and right. So it's also a function of y. So that's really what comes in here. And then there might be some unknowns associated with the u field. Okay, so that's essentially what I would expect to happen. Okay. And then on the v field, there would be sort of a field that says, okay, this node can move up and down. And well, this node can move up and down. Also a function of x and y. So if I move this side, it still goes up and down. So I can move in x and in y, and any point can have a displacement up and down. So this is what this the v field will do for us. It's the displacement in this y direction. Okay, and that's the unknowns qv that we have there. Beautiful. So this is essentially what we would expect to see. Okay, so I just want to write down sort of an intuition for us, based on what if I just write a compact form for this. I could write this as the summation I from 1 to 4 of n1 ni qi. Can you see that? So I could write it like that maybe as a compact form. This is not a 4. What is this for? 3. I'm in my head now on the 1 to 3. 1 to 3. Okay. So I could write down a compact version of this maybe to say here's 8 nodes. So maybe if I follow this sort of similar kind of argument, there might be some displacement from 1 to 8 for the 8 nodes of ni q ui. That's beautiful. Okay, so that is essentially what that would tell, but how this field would look in the x direction, how things would just move left and right, but everywhere left and right. If I were to just flip this on its side, then the x would be up, and I could use that same description of a field to tell me how things are moving still along this x-axis. If I just rotate this like this, let's say the x-axis points up and down, then that will tell me how things are displacing up and down. And if I were to relabel them then to say let's flip this like it's x and y, this little cube like I've mentioned. So this could tell me how things are now moving still in this x direction. But if I were to label it just differently, to say let's label it y, hypothetically, yeah, then I could actually use the same description of these shape functions to tell me how things are moving like this direction as the same as how things are moving this direction. So why not do that? That's like the simplest thing we could do. Say, but maybe we could use the same shape functions, okay, because they're still going to vary as a function of the things. We're going to talk about these shape functions in a second, and then essentially say we have now the variables qvi working with that. As a reminder here, the shape functions n I was a function of only one variable psi. So what would the expectation be in the 2D case? Well, in the 2D case, I would expect maybe if I take this rectangle, remember what we had is in this local coordinate system, we had some axis in the middle of this thing. So maybe we have some axis here in the middle of this thing. And this is maybe still psi, and this is maybe another variable. Let's call it eta. Okay, so that's another variable there. We know that psi went here from -1 to 1, so expect maybe 1 is 1 to 1 here. And maybe on this side, it's for eta, y0 also minus 1 to 1. But now I have essentially a shape function, which is not only a function of psi, but now it's a function maybe of psi and eta. Okay, so the shape function here, ni, is now a function of psi and eta, of two variables all of a sudden. Beautiful. But now what I have is I have a beautiful description of what's going on. Yeah? So this really allows me to say, well, fantastic. This is a description for how the displacement field could look. Okay, so make sure I'm recording there. Okay, so this is just to make sure that this displacement field, this is how what we might expect. This is now for a thing with 8 nodes. And the mid side might be at a psi of 0. And this mid side here would be essentially at an eta equals to 0, but at a psi minus 1. So that's, look how beautiful that kind of description is, of taking our global thing and moving it there. How do I map this, the link between these two things? Well, it's the isoparametric formulation. So let's do isoparametric quickly. Isoparametric. Okay. So for the isoparametric formulation, I could have then say, well, x is a function of the sum from 1 up to 8 of ni, yeah, and then each of these nodes has associate coordinate. So I'm just going to write it like this. So this node is xi, yi, okay, and we have maybe some numbering. I'll tell you what the numbering is for element in 2D. This is just convention again. It's not because it has to be, it's just because traditionally this is what it is. Numbering 1, 2, 3, 4, 5, 6, 7, 8. So that's typically the numbering that we have for a quadratic element in 2D. But that is essentially x, ni, and all the xi's. Okay? But I can't just have one, like here I had one field because it was only in x. I need to have also an idea of how things vary in y. It's a function of yi. And maybe what I want to do is, not to be too sloppy, but to be explicit here. What is xi and y a function of? Like we've done here. I want to just make it explicit. What would our expectation be? Well, x would be a function of psi, eta, because I can move up and down, and every point can still move left and right, or left and right, yeah, and essentially all the xi's, or x's. I can maybe write it as this bar. Maybe I'll just put that bar back on there like I've done previously. So let's call it a bar, so that they distinguish that from the nodes. And the y would also be a function of psi and eta. And so there's essentially a relationship here between that. You see that? Beautiful. So this would be my expectation. So just taking what I've learned from 1D, that I have a description for a summation of ni xi, in terms of how the isoparametric would look, that there's now essentially just a description for the x and the y. How points would move up and down or left and right. And now I've got the two fields to capture that. The two fields to capture the displacements in respectively the x direction and the y direction. Okay. So let's stop this video and then let's think about what strain is going to entail.